Today, I'm going to be taking up this paper called Simultaneous Detection and Segmentation. And it's by a bunch of guys called Hariharan for starters. And he has a bunch of papers in this domain, and they have proven to be quite influential, barring this one, which is influential as well. But there are many more other than this. And so we'll be talking about a couple of things today. The background, the motivation behind the paper, certain evaluation metrics that were taken into consideration while writing this paper, the algorithm, which is basically the main crux of the paper, some of the experimental results and future work that was carried out which in conjunction with this paper and certain references that are used while writing this presentation. Right. So a couple of prerequisites which are not hard and fast, but I'm assuming it would be helpful to know about some of them. So support vector machines, a bit of idea about object detection and convolutional nets would help, and a bit of knowledge about how RCNNs work is will be helpful, but it's not really necessary in this case. I'll try to go over it as much as possible, and if anyone has any doubt regarding it, they can feel free to kind of interrupt me and ask away. Right. So the basic idea. So why did these guys write this paper? What's the problem they're going to solve with this paper? So given an image, what semantic segmentation does at its heart is classify pixels in an image belonging to a certain class. It assigns class labels to a pixel, which basically means suppose I have an image of two dogs, or rather, this illustration should make it really clear. If I have an image which has two dogs and a cat, I assign each of the pixels in this image which belongs either to the background, to a dog, or a cat. That's what semantic segmentation does. And that gives you a picture like this, where each and every pixel is assigned to a class. A class in this case will be any object that is in the image. And that's what classical semantic segmentation does. But the task at hand that they're trying to solve is by a novel method called simultaneous detection and segmentation, or SDS, which is how it's abbreviated, where we seek individual object instances, unlike classical semantic segmentation. And what this means is basically this. What semantic segmentation does is in this image, it does not distinguish between the dogs. So it both these dogs are treated as the same entity. This is a dog, this is a dog. There's no differentiation between the two. But what instance segmentation is doing is it's saying that, okay, this is one dog and this is a separate dog. It treats them as two separate entities, which normal semantic segmentation doesn't do, right? And that is what we are trying to do here. Okay, so an overview is this. So it's known that convnets are used for detecting features in an image, determining how edges are located, and so on and so forth. But so it's basically the same idea we're using here, and we wish to use that idea of convnets here as well. So we use CNNs to classify category independent region proposals. And what this means is that we're trying to make or formulate boundaries around our images, around the background, to distinguish between what an image is, what an object is, and what the background is in the image. And that's what we'll be using CNNs for in our task. And the need for this paper and the need for this algorithm, it's basically going an improvement over whatever was existing before this. And it's quite a jump from whatever was before. There's a 10% increase from state-of-the-art semantic segmentation models that existed before this. And that's a huge leap. Right. So where image segmentation differs from traditional bounding box algorithms is this. As you can see, bounding boxes offer a coarse localization. They're not smooth. They just draw a box around where the object is in the image. But instant segmentation gives a smoother boundary around our object or segmentation as a whole. And this is what we wish to achieve. And it's much more accurate than bounding box detection for certain tasks, which is very dependent on what you want to do with the image later on. So before we begin formally introducing the algorithm, we need some metrics which evaluate our model, and we introduce some metrics which are specifically geared towards our task. And but before that, I'd like to kind of touch upon what already exists, and that's precision and recall. So some of you might be familiar with this, but nevertheless, I'll go over it once. So I'll skip over the formal definition of what precision is. It might seem a bit complicated in the beginning. So I'll go over the simpler one and a bit of idea of what the formula actually is. So precision is basically a measure of the false positives that are diagnosed in a sample space. So as you can see, we're trying the lesser number of false positives. So TP corresponds to true positives, and FP corresponds to false positives. So the lesser the number of false positives, the higher our precision is. And the greater the number of false positives, the lower our precision is. Basically accounting for, so precision basically accounts for the number of false positives that we encounter in our data set. Similarly, we define recall. Again, I skip over the definition. It might seem a bit convoluted for some. And I look at the easier part, the fraction of false negatives diagnosed. So as you can see, it's the same idea as precision. Instead of false positives, we have false negatives in this place. The larger the number of false negatives, lower the recall, and vice versa. Now that we have precision and recall, it's useful to know how we interpret the curves that we plot corresponding to these measures. And before I tell you about this, there is the first line. We give the importance we give to either precision or recall is very use case specific. And so this, what I mean to say by this is, suppose we have a spam classifier, email spam classifier, and in this case, we would rather diagnose. We care more about falsely classifying spam email as non-spam and not the other way around. That would not make sense. You might miss some important emails in that case, and that means that we care more about classifying false positives, and hence logically you would give more importance to precision over recall. And that's what I mean to say when I say it's very use case specific. Now, in an ideal scenario, our precision and recall should be one, which means that there's no false positives diagnosed, no false negatives diagnosed, and that's hardly ever the case. But a scenario that would seem ideal is a high precision and a high recall for a large part of the journey. So if I look at this curve, the purple curve over here, FR and CH, they are close to 1. So an ideal scenario you would imagine to be towards the top right corner of the graph. But over here, it's this way for a large part. And that's somewhat ideal. This is what you would want to look at when you say that you have a good model at hand. But a bad scenario is where both the quantities are low. That means you're diagnosing a high number of false positives as well as a high number of false negatives, which is the red curve. There's like a downward trend, and there's like low precision, low recall, and that's not good. That's not what you would want to see, and you would want to go back and diagnose what exactly is wrong with your model. So using precision and recall, we define a new metric, and since this is a non-standard task, and we wish to evaluate it better with a metric that is geared specifically towards what we're trying to solve. And we define this quantity as average precision or AP. And the way we define it is as the area under a precision recall curve. And there are two types of APs, APR and APB. APR corresponds to the average precision for region boxes. And region boxes are basically masks that we create to differentiate between the object and the background. And APB for bounding boxes is the boxes that are surrounding an object in the image. As we saw in the image of the dog, this is a bounding box, and that's what we call that's what is the metric corresponding to APB. Right. And extrapolating this APR and APB, we can vary this over a variety of thresholds. Thresholds is basically the overlap thresholds for which we uh, kind of compute the region, how much our boxes are corresponding to the ground truth and how far off they are. And on varying thresholds, as you can imagine, we'll have multiple PR curves. So a PR curve corresponding to threshold 1 to threshold 2 and so on and so forth. And as you can imagine, if you have a curve in 2D space and you start plotting it for multiple inputs, you're going to trace a surface, right? So that's basically a solid of revolution that you create when you have a curve and you start giving it multiple inputs. And that's what I mean to say here when I say that a PR curve in R square, which is basically on a plain graph paper, traces a surface in R cube. So I go from a 2D plane to a 3D plane. And here we define APR volume and APB volume, which is the same idea as before, except I'm doing it over a variety of thresholds as opposed to one. And a neat property of these metrics APR volume and APB volume is that the area under the volume under the surface is one. And that's easy to imagine since basically at its heart, precision and recall are probability distributions, right? So the volume does have to be one, otherwise it won't be a probability distribution anymore. And lastly, intersection over union. Most of you might be familiar with it, but I'll still go over it. And this is a pretty nice visual, which kind of explains what's going on. And it's basically the area of overlap over the area of union. So the green box here corresponds to the ground truth, which is what you should get. Ground truth is what you would get in an ideal case, and red is your prediction that you've made. Now, area of overlap, basically how much these boxes overlap over the area of union of these two boxes. That's the intersection over union. And it's pretty self-explanatory from the name as well. Right. So now the algorithm, which is the main part of the paper. So we have four major steps in the algorithm. It's proposal generation, feature extraction, region classification, and region refinement. And this diagram kind of highlights what the entire pipeline of our algorithm. So I'll explain it in a couple of sentences here, and we'll go into further detail later in the first upcoming slides. So suppose we have an image of a baby boy here, and we perform proposal generation. Basically, we propose a number of bounding boxes around the boy, saying, okay, this is a region where something could be present. There could be some features here. There could be a place to search for meaningful things here. Proposal generation. And from these proposal generations, we extract features. That is feature extraction. Now, over here, you can see that there are two separate images, right? And the difference between the two is pretty simple. This image has a crop figure of mainly focusing on the boy, but the other image has the background completely masked out and only the object in the scene. And using these two images, we feed them into separate convolutional networks, a box CNN and the region CNN. Box CNN because it's a box around, we're focusing on the box, on the image that the box contains, which is the object, that is the boy in this case, and region CNN because we only focus on the foreground of the image rather than the background. And since these are two disjoint networks, we concatenate the two here, the outputs from the two, and we get something better here. We classify the regions, we extract feature vectors here, we classify the regions as belonging to the object or belonging to the background. And then, as you can see, the segments over here are not really smooth. And there has to be some refinement that improves on this. And that's what is called as region refinement, where we improve upon our segments that we created. Right. So proposal generation. And proposal generation is basically trying to generate a couple of boxes or regions where our object could lie in the image or what could be important features in the image. So, right, since we care more about the APR metric, because we're talking about region masks here, we uh, use MCG, a technique called MCG, an algorithm. It's called multi-scale combinatorial grouping, which I won't be covering in much detail here because that's a topic separately of itself, and that's a topic for another day. But I'll try to explain what it does in a nutshell. And this visual representation is pretty neat. It kind of explains the entire process with pictures, without much words, and it should. I'll try to walk through this. So I have an image of a koala on a tree, and I have it on different resolutions, a small size, a medium, and a normal size. And then I construct segments on these images, on the different images of different resolutions. I rescale all of them to the same size with the segments. And I combine all the segments into a single image. I superpose all of them. And then I combine these segments with the original image to get object proposals. That's what this does. And MCG is used to generate these region proposals because it outperforms the standard technique that most papers use called selective search. And there's like a not significant improvement, but nevertheless, it's an improvement. It's an improvement of 0.7%, and that's enough to justify its choice in this case. The next step in the pipeline is feature extraction. So we use a technique similar to what is used in RCNNs, if you're familiar with them, is used here. But in the fact that differs between SDS and RCNNs is this: RCNNs have used selective search for generating their region proposals, whereas SDS has used MCG. But the idea is the same. We use the region proposal candidates from the previous step, which we got from MCG, and then using these boxes, we try to extract feature vectors from each of the region proposals that have been generated. And we try to split, as you remember from the image of the pipeline, we had two separate images here, one with the box around the object and one with the region masked out. And that's exactly what I've written here. Region box as it is. So we construct a region box around the object corresponding to this image, and a similar region box but with a masked background. So masked background, right? And these are the two boxes, region boxes, that we try to extract feature vectors from. And from here, we define three feature extractors, A, B, and C. So A is what we call the naive feature extractor. And the reason is simple for calling it naive, because we don't really use too much of our brains here, and we kind of go on a down a simple route here. So what we do is we take the two images, the with the two separate types of region boxes, and we concatenate the feature vectors from both the bounding boxes. So the feature vectors that I extracted from the region box, as well as the feature vectors that I got from the mask background image. I concatenate the two, and from here I get another image, which I and from here I establish my baseline model. I after concatenating the feature vectors. So this is the most primitive model, hence it's our baseline. Now we define feature extractor B. And over here, how it differs from A. So the need for uh, defining another extractor was this, because we need two separate okay, let me just go over B and explain why we did this. So our idea here is to use another fine-tuned network to extract the second set of feature vectors and predict region overlap. So what this means is that there are two separate uh, conv-nets that are training on our images. One is for the one with region boxes, and the other is for the one with the mask background. And the reason we do this here is because um, our network has to be fine-tuned for a certain task, because in one case it might be that the convnet is extracting features from our background, which is not what we want. It's not part of our object, right? So we don't want it learning features that are extraneous, and hence it would make sense to define another network that does the same task and goes on to extract feature vectors. And now that's our model extractor B, and we define our last extractor C, which is the novel point of this paper, a novel architecture which uses a single network having two pathways, one for the crop boxes and the other for the mask background. So this image should make it clear. So over here, I have an image, the same image of the boy. I propose a region box for the image, for the object. I have the region box and I have the one with the mask background. And here I have two separate convolutional networks, one for the region box and one for the part with the mask background. And as you can see, they have exactly the same architecture. There's no difference between the two of them. But this is where it differs from B. What B said was that we have another fine-tuned network to extract the second set of feature vectors. So the architecture of network, if I consider this to be network 1 and this to be network 2, this is network 2 would not be the same as network 1 for in the case of B. But in case of C, both of them are exactly the same and they're disjoint. They're not connected together in any which way until the last step. And what we do in the last step is we use the outputs from the fully connected networks, we concatenate the two, and then we pass it on to our classifier. So now that we have a concatenated image from our feature extractors, from A, from B, and from C, we pass it on to another classifier, which classifies the region as to belonging to the object or belonging to the background. So we use some extracted feature vectors from our image to train a linear support vector machine for identifying whether an image is positive overlapping or negative overlapping. And positive negative basically means positive corresponds to belonging to the object, the pixels belonging to an object, whereas negative corresponds to the pixels belonging to the background. And this is what we do with the linear support vector machine. And now what we do is that whichever regions are overlapping with a ground truth of less than. So for training the linear SVM, we use a certain constraint that whichever region overlaps by less than 20% as negative is discarded. And after discarding this, we have a little bit more refined set of feature vectors from where we re-estimate our classifier. And this re-estimation is done for each set, and we pick the one with the highest scoring MCG candidate, which overlaps by more than 50%. And we retrain these classifiers again, and on the new positive set, and empirically that proved to be a much better technique, since it gave since it gave some improvement in the accuracy. And after doing all of this, after getting the classifying regions, we performed a strict non-maximum suppression. Non-maximum suppression. So let me go over this for those of you who don't know what it is. Basically, when we generate region boxes for objects in an image, there might be multiple. There can be multiple of them, but we wish to choose the one which has the maximum amount of overlap with the ground truth box. And that's what we do in non-maximum suppression. Everything that's not the max is suppressed or discarded with a zero region overlap threshold for multiple overlapping regions. That's basically defining NMS in some sense. Now, since now we move on to refining the region. So in this step, we basically generated segments on our image, which are not so refined as we saw over here. Not so refined, but okay, we do have segments here, but we wish to improve upon that. And for that, we do region refinement. So since we did not take into consideration what the class is while, you know, classifying the pixels as belonging to class or not, we never specified, okay, this pixel belongs to the background, this pixel belongs to the boy. It was all independent of the class. So this means that there's some room for error here. And there are two types of errors that might occur. That's undershooting or overshooting. So undershooting basically means that there are some missing parts of the object that have not been counted in our segment. Whereas overshooting means that there are some extraneous bits or extraneous pieces of the background that we have considered into a segment for the object, which should not have been there, and hence overshooting. So to fix this problem of either undershooting or overshooting, what the authors proposed was a fix where they kind of divided or discretized the bounding box to a 10 by 10 grid, and on which they trained a logistic regression classifier. And each cell was trained on this, and this was trained for predicting whether or not each cell belonged to the foreground or the background. And as you can imagine, a 10 by 10 grid is not really very fine, and it's going to give something which is coarse, like this. A 10 by 10 grid would give a really coarse, mapping of the object. And this is not exactly ideal. It's very pixelated. You would want something that is much smoother and covers all the contours and shapes of the object that are present in the image. So because of this, we need a bottom-up region candidate. And now there's a second stage to this, in which we combine coarse masks with the region candidate to give a more refined mask. So this coarse mask, this region candidate combined, we get something much better. Do this again, we get something slightly more better. And we superimpose that with the original image to get a much smoother and refined segment. So The technique used here is something called is done by generating superpixels, and superpixels are basically pixels which have the same pixel, a bunch of pixels in an area which have the same characteristics, and characteristics could be anything. It could be something like pixel intensity, it could be proximity, it could be anything of that sort. And the way superpixels are generated is by something called the SLIC algorithm, SLIC. That's simple linear iterative clustering. And what this does is it generates super pixels by clustering a bunch of pixels in an image based on their color similarity and how close they are or proximity in the plane of this image. So as you can see over here, we were undershooting since we did not consider a segment which was actually supposed to be there in the final image. And you can see there's a much larger refinement, a much better segment that we've produced. In this case, we were overshooting, counting parts of the background to be parts of the image, parts of the object. And here we have a much refined segment of the car. And similarly for the cat, you can see that there we were undershooting here, and we have refined it to something much better. So some experimental results here. Uh, so all these systems were trained using the Pascal VOC dataset, and the segmentation annotations were from the SBD dataset, which is the semantic boundaries dataset. And as you can see, so over here we compute the volume metric APR volume by averaging APR over a bunch of thresholds, 9 thresholds to be precise. And the reason we do it over a fixed number of thresholds is this: we cannot have infinite number of thresholds. So you won't exactly have a surface. That's purely theoretical. You average it, and that makes sense. Since you're doing it over a bunch of curves, you would have something that corresponds to an average volume over 9 thresholds. And here our baseline model is called O2P, or second order pooling. And you can see the stats for yourself. APR is 25.2 over here. And for our models, 42.9, 47, 47.7, and 49.7. And C plus ref is basically C with the region refinement. And this is the C, and C with some region refinement is what has been used here. And there's a significant jump in all the categories. So that's like really cool. And you can see that we have not overfit to any particular regime by looking at the PR, by looking at the change in APR and over the varying thresholds. And you can see there's always an increase or some form of increase for all of the cases, B, C, and C plus refinement. And that indicates that there's no overfitting. And right, so we generate some diagnostic results, some diagnosis or diagnostic tests, rather to say, which kind of account for the errors that are produced. And one of them, the most prominent one, being something called mislocalization, which they have defined in this paper. And before I begin with the definition, I would like to mention that they have said mention something about a threshold, the overlap threshold again in this case, a strict overlap threshold and a lenient overlap threshold. Strict one being zero point 0.5, so it has to be 50% overlapping with the ground truth box or segment, and a lenient threshold, which is zero point 0.1 for region overlaps. So the way we define mislocalizations is the detections which count as true positives under the lenient threshold. That means they pass the lenient threshold test, but as false positives under the strict threshold. False positives under the strict threshold meaning they have been wrongly classified because of the lenient threshold. So this means that there is some mistake somewhere down along the way, which has caused this mislocalization, so as to say. And this is a major fallback, causes a major fallback in accuracy, and that's by 16 points, and that's pretty huge. So fixing it is, of course, going to be a priority, or any way to fix it. So in the paper, they have not really mentioned how they have fixed mislocalization, but they have given results after fixing it. So C plus ref, that was our original best model with the refinement, with no mislocalization, uh, we get something like the green curve. And after correcting the mislocalization, we see that this is miles apart from the refined model as well. There's a huge jump. So improvements in this feature vector, feature extractor improves upper bound to a certain extent because we start making fewer misclassifications. And as you can see from this table, that once our network improves, our feature extractor improves, the gap between mislocalized, the gap error caused due to mislocalization starts reducing as well. So C plus ref was supposed to be our best one, and we have a 15.8% loss here. Whereas with A, which was supposed to be the most naive feature extractor, we have a higher loss due to mislocalization, which is 20.1. And all of these are upper limits to what the accuracy could be, uh, considering that we remove all mislocalization in the image. And okay, so now APB and APB volume, these are not exactly tasks which are uh, solved by the SDS algorithm, because we do not predict bounding boxes, but we instead predict segments. So these region classifiers were trained for the bounding box detection task in this case. And here we have two different baseline models: RCNN, which uses selective search, which is the standard RCNN, and another RCNN, which is trained, which has the feature extract, which has proposals generated using MCG. So there is some improvement between the two baseline models itself, but the results from our feature extractors also have a huge jump. So a 2.9% jump here, uh, and a 2.2% jump here from RCN and MCG to B, and B performed the best. And it might seem surprising in the beginning as to why B has performed better than C when this was not the case before. But it seems logical that the authors argued that this was because our task is more geared towards solving SDS rather than predicting bounding boxes, and it's fine tuned for that. So as you can see from this graph, the curve for B has always been ahead, more or less ahead of C, and it has done much better than what our baseline models do. And the last one being pixel intersection over union. And what we've done is converted the output of the C refined model to a pixel level label, category labeling using support vector regressors. And the idea is the same as what support vector machines would do, yeah, in some sense. And we can kind of ignore that for now and just look at the statistics. There is again a jump from the baseline models, a significant jump, around like a 5% jump from the baseline models. And that kind of justifies the work that these guys have done. And it's a much larger improvement than what was considered to be state of the art before this paper originated. So some influential works that came up after this paper, inspired from this paper, are really prominent today in the field of computer vision, like Mask RCNN, YOLO. YOLO had several versions after that: V1, V2, V3, V4, and FCNs for semantic segmentation, amongst many others that have been using this idea. And these are the references that I used here, and uh, that's kind of it. Thank you. So does anyone have any doubts or any query? Oh, there's something in the chat. No, YOLO wasn't discussed. Why don't 2D models perform not so well on 3D models? That's because 2D models are optimized for the task of, doing things on 2D models, right? It's kind of fine-tuned for that, not for 3D data. So if you have explicit models for 3D data, it would perform well on that, but not on 2D data. It depends on what task your model is trying to solve, right? Did that answer your question, Prabhav? Okay, cool. Is there any other thing?
Actually, I also want to know, like, while reading about the model, uh, were you able to find some source code and mess around with the model, or like get
Um, right.
architecture more?
So the source code for this is written in Cafe, and I have absolutely no idea of how to use that, and neither have I used it before. There's no implementation for this, unfortunately, in or open source implementation at least I could find in PyTorch or TensorFlow.
Actually, this is the problem which I was also facing. Like, uh, there is, like, for the popular frameworks, like you said, like PyTorch, TensorFlow, FastAI, etc.
Right.
The source code is really not available, and what little I could also find was in Cafe. So in that case, like, what should one do? Should one actually learn Cafe and then adapt oneself?
Uh, I don't know, honestly. I mean, I don't see why there's point in learning Cafe for the explicit reason that, see, most of the things have their implementation